Hello everyone. So today we'll start with the next lecture of the module pre-stressed concrete. So in the last lecture we have seen problems on stress method. So today we'll continue with the second method, that is the pressure line method. So let us just go through the various methods. So basically there are three approaches to analyze a pre-stressed member at transfer and service loads. These approaches are based on the following concept. First is your stress concept. It is also called as extreme fiber stresses. The second is your strength concept, internal resisting couple method, or it is also called as the pressure line method or the force concept. So remember, these are the different names for this method. There is the pressure line method. It is also called as the strength concept, internal resisting couple method, or the shift of the pressure line. And the third method is load balancing method or the load balancing concept. So that we will see in the next lecture. So in this lecture we are going to do some problems on pressure line method, and we will see what is this pressure line method. So the stress method is basically used to compare the calculated stresses with the allowable stresses. So we find out the resultant stresses in that method so that we can compare it with the allowable or permissible stresses. So let us see what is a pressure line. So pressure line is nothing but basically it's a locus of the point of the application of the resultant force in any structure. That is nothing but your pressure line. So it is nothing but the locus of the point of application of the resultant force. So let us just go through the section which I have shown in the figure, longitudinal section. So at any given section of a pre-stressed concrete beam, the combined effect of the pre-stressing force and the externally applied load will result in the distribution of concrete stresses that can be resolved into a single force. So this single force is nothing but the resultant force, and the locus of the point of application of this resultant force is called your pressure line. So this pressure line is given by the formula, the distance, that is m by p. This is only for the straight cables. So you can see I have shown two longitudinal sections, one for a parabolic cable and one for a linear cable. So this is how the pressure line looks like. So the distance from the tendon is given by E, which is given by m by p, and this equation is applicable for straight cable. So basically what happens in your pressure line method, so you have this pressure line and the other one is called as the compression force. So the pressure line or the P force is nothing but the tension in the tendon, and the C line or the compression force is nothing but the compression which is generated in the concrete. So what happens before the application of the load, so the C line and the P line, they are at the same point or they coincide, but when the member is subjected to external loading, so the P line remains the same, but there is a shift in the C line. C line means the compression in the concrete. So this shift is nothing but your distance E, which is m by p. So this shift we have to find out in this method, which is given by m by p, and then we have to plot the pressure line. So I hope it is clear now what the method is. So now let us go to the actual problem. Okay, I'll read the question. A pre-stressed concrete beam of section 120 mm wide and 300 mm deep is used over an effective span of 6 meters to support a UDL of 4 kN per meter, exclusive of the self-weight. So they have given that is exclusive of the self-weight, that means self-weight is not included in that. The beam is pre-stressed by a straight cable carrying a force of 180 kN and located at an eccentricity of 50 mm. Determine the location of the thrust line in the beam and plot its position at the quarter and the central span section. So what we have to do, we have to find out the location of the thrust line and we have to plot it at the quarter and at the central span of the section. So let us see what is given in the question. I've drawn the cross section. The width is 120, depth is 300, and the longitudinal section. So the span is 6 meters and eccentricity is 50 mm, and your external load is given as 4 kN per meter. So what we have to find? We have to find the thrust line at the quarter span and at the central span. So let us start with the first step is to find out the loads and bending moments. So first we'll find out the dead load of the beam WG, which is section into the density. So section dimensions into the density, which is given by 0.864. So live load is given in the question, which is 4 kN per meter. So the total load becomes 4.864. So next what we will find out, we'll find out the moment at the quarter span and at the central span. So it's a simply supported beam of span 6 meters. The total load acting on the beam is 4.864. So for the central load it is nothing but WL square by 8, which is 21.89. And for to find out the moment at the quarter span, first we'll find out the reactions. So reactions is nothing but WL by 2, which is 14.6, and at the quarter it is 16.43. So this we have already done in the previous problem, how to find out the moment at the quarter span. So we got the moment at the central span as well as the quarter span. So next step is to find out the location of the pressure line. So location of the pressure line is given by M by P. So at the support there is bending moment is 0, so it is 0. At the quarter span it is moment at the quarter span upon P. So moment at the quarter we have already found out 16.43, that is in kilonewton meter. So if you convert that into Newton mm, it is 10 raised to 6 upon P is 180 into 10 raised to 3. So your shift of the pressure line is 91.3 mm at the quarter span, and at the central span it is 121.7. So M center means bending moment at the center, which is 21.89. So now you can see the diagram how to plot the pressure line. So you have to first draw the longitudinal section of the beam. You have to show the tendon position, and from the tendon position this is the shift of the pressure line. So as I have told you before the application of the load, the P line and the C line they coincide, but after the application of the load there is a shift in the C line, which is nothing but the pressure line. So this shift is given by this E, or you can say it as A. In some textbooks it is A, which is M by P. So at the quarter span I have plotted 91.3, and at the central span it is 121.7. So you have to join these distances from the tendon. So this is nothing but your pressure line. So now let us go to the second question. Okay, so I'll just read the second question. A rectangular concrete beam 100 mm wide and 250 mm deep spanning over 8 meters is pre-stressed by a parabolic cable with pre-stressing force of 250 kN with 0 eccentricity at the supports and 400 mm at the midspan. The beam supports a live load of 1.2 kN per meter. Determine the position of the pressure line and plot it at the quarter and the central span. So here also the given data is almost the same. The only difference is the profile of the cable. So here the profile is parabolic, and the previous question it was straight. So now let us see how to find out the pressure line when the tendon profile is parabolic. So I had given you the equation that was for straight cable. So let us see how it is different. So the first step remains the same to find out the section properties. So we will find out the section properties, that is area, y bar, I and z. So since it is symmetrical, so you can find it easily. And then loads and moments. So dead load of the beam is again cross sectional dimensions into density, and live load is given in the question 1.2. So the total load is 1.8. So similarly you will find out the moment at the support is 0, moment at the quarter span is 10.8, and moment at the center is nothing but WL square by 8, which is 14.4. So now to find out the location of the pressure line, third step. So now we can see that the profile of the cable is parabolic. So we will use the equation of a parabola, that is y is equal to 4hx into L minus x upon L square, where L is the total span and h, remember, is the highest eccentricity, that is at the midspan. So that is your h. Now we have to find out at the quarter span. So at the quarter span let us say y equal to E. So we don't know. So at the quarter span we'll find out 4 into h is your 40, and x is at the quarter span. Now this is important, your x distance at the quarter span is 2 meters. So you will substitute that value of x and you will find out the distance at 2 meter, that is 30 mm at the quarter span. So now we got this distance from the equation of a parabola. So now we will find out the stresses at the support, quarter span and at the mid span. So at the support the stresses are where eccentricity is 0 and your moment is also 0. So this will become 10 and F bottom is also 10. So these two terms will be cancelled since your E is 0 and M is 0. So next is at the quarter span you have eccentricity as 30 mm which we have calculated and your moment is 10.8. So your F top becomes P by A minus PE by Z plus moment at the quarter span by Z. So which gives a value of 13.17. Similarly for F bottom it is P by A plus PE by Z minus moment at the quarter span upon Z. So we got the value of F top and F bottom. So now what we will do, the next step is to find out the resultant stress. So remember this, after this step what you will do, you will find out the resultant stress. So how will you find out the resultant stress? So this is nothing but your resultant stress diagram. Top is 13.7, bottom is 6.83. So if you want to find out the location of the resultant, so you can use this formula, x is equal to a plus 2b upon a plus b into L by 3. So this is how we find out in case of a trapezium. So where a is the shorter side and b is the longer side. So with the help of this equation you will get x is equal to 138.21. So the resultant is acting at 138.21 from the bottom. Similarly at the midspan your eccentricity is 40 which is given in the question, m is 14.4. So your f top becomes P by A minus PE by Z plus moment at the midspan by Z. So this comes out to be 14.23 and F bottom comes out to be 5.57. So I have just plotted this and the resultant stress diagram looks like this. So your resultant again is found out by that equation, a plus 2b upon a plus b into L by 3. So it acts at 142.63 mm from the bottom. So I hope this is clear now. So now we can actually plot the pressure line. So let us see how the pressure line for this will look like. So this is the longitudinal section of the beam. Depth is 250. So I have divided into quarter intervals. So 2 meters, 2 meters. So at first we will see the distance at the midspan. So at the midspan the resultant stress is acting at x is equal to 142.63 from the bottom. So I have plotted this value 142.63 from the bottom, and similarly at the quarter span I have plotted this at 138.21 mm from the bottom. So now if you join this you will get your pressure line. So this is how you will find out the pressure line in case of a parabolic profile of the cable. So I hope this is clear now. So this was the second method, that is your pressure line method, and we have solved two problems, one for linear and one for parabolic. So in the next lecture we will see the third method, that is load balancing method. Thank you.